the Uranus. Okay, so welcome to the Uranus video. In this episode, we're going to start by looking at the semi-major axis, which we all know to be the longest distance, the sum of the longest distance and the shortest distance from the Sun of Uranus divided by 2, finding the average distance from the Sun, which we call the semi-diameter of the orbit, assuming that it will be in a perfect circular shape. So we have that calculated. As you can see, a plus p, which is 20.0965 plus 18.2861. The a is aphelion, the p is the perihelion, what you call the abscess and the periapsis. You divide by 2 and then you get your semi-major axis z, which is equal to 19.1913 astron per unit. And then our conversion to meters, because we know in astronomical units, it's in terms of the distance between Earth and the Sun, as we looked at the last episode, which was to planet Earth and beyond. I encourage you to watch that one. It was a very exciting one. So to convert to meters or kilometers in this case, we just divide the astronomical units by that rate, which is 6.685 times 10 to the power negative 12 astronomical units, which you equal to 2,870,800,299,000 meters. That's why I find it says 299,000 meters, which is kilometers basically. And then if you convert it to terameters, which is basically the 2 trillion, so it becomes 2.87 trillion meters, which is basically terameters if we use the scientific prefixes for the international standard of units. So you can use the same conversion rate to find the aphelion and the perihelion in terms of meters, in meters. So you just divide like what we did with the where it says zkm, z subscript km, which is z in kilometers. You do the same thing and then you get your meters for the perihelion and the aphelion. Okay, now we move on to eccentricity of Uranus's orbit. I think we now know what eccentricity is. If you don't know, you can read that note at the top right there in white, so that you can understand. And you know the formula for eccentricity is epsilon is equal to 1 minus that fraction there. And remember, the a and the p represents the aphelion and the perihelion, that fraction of the aphelion and the perihelion. And then we have that epsilon being equal to 1 minus, and then we substitute the a and the p with the aphelion and the perihelion, which we saw in the previous slide. That's 1 minus 2 over 20.0965 over 18.2861 in brackets plus 1, which will give you 0.047167205, where the eccentricity epsilon will be equal to 0.0472, correct to 3 significant figures for accuracy, which means it's actually very close to a circular shape, not what you're seeing on that diagram there. That one is more to an oval shape, but with this value it's close to a circular shape. Okay, so before we look at Uranus orbital period, I would like us to look at how we derive these expressions that we're going to be using, or the formulas that we're going to be using in terms of what is in Kepler's third law, or deriving them from Kepler's third law. So as you can see, the Kepler's third law talks about the orbital periods of the planets being directly proportional to the cubes of the semi-major axis of their orbits, and we see that is expressed in the formula T squared over I cubed is equal to 4 pi squared over gm. That's the equation or the expression for Kepler's third law, which shows the proportionality. But what we are focusing on is what is encircled in those with the yellow Okay, I'm not sure if we call them circles or loops or whatever they are. Just those boundaries that sort of encircle, let's just say encircle the expressions that you see, one with t as the subject of formula, which is the orbital period, and the other one with the z as the subject of the formula, which is the same major axis. Don't be confused by the r and the z. It's basically one and the same thing in this case. The reason why I use z is because the r, the symbol r, I usually use it for the radius, so the z is the one I'll use for the same major axis, so that we don't confuse the two. So what I was saying is we get these formulas from the proportional from the expression of the proportionality of those two variables, which are the period and the same major axis. You can use that one with z, the same major axis formula. You can use it also to find the same major axis, but you need the period in order to find that. Instead of using the aphelion and the perihelion, like we did, the average stuff, yes, you can use that formula and still get the same answer, or approximately it's the answer, which is what we got previously. And then now we're going to be looking at the orbital period using that formula that you see at the left side there. Okay, so now you see where we're getting the formula. T is equal to 2 pi multiplied by the square root of the cubed of gm. The g is the gravitational constant, and the capital letter M is the mass of the sun. As you can see, the values are there. The gravitational constant is 6.674 by 10 to the power negative 11, multiplied by the capital letter M, which is the mass of the sun, which is 1.989 by 10 to the power of 30 kilograms. And then the numerator there, which is the z cubed, you can see the values there. If you have forgotten, you can refer to the first slide where we calculated the same major axis, where you just take is the same major axis and then you cube it, but you take it in meters. Yes, because these calculations we use the international standard units in order to get a uniform value that everyone can understand. And then we get our answer, which is there in seconds, and then we divide by 60 seconds, by 60 minutes, by 24 hours, by 365.25 days. Remember, 25.25 means a quarter. Yes, around 365 and a quarter days, as I explained in the Earth video. And then we approximately get 84 years. These are in terms of Earth years, so that we can understand the period in terms of our time. So if you don't understand that, you can refer to the previous videos in this series, Planets in Our Universe, and get to understand what I mean by Earth years. But basically, it's relative to our time. Okay, so now let's move on to calculating the orbital speed. We're going to be looking at the average orbital speed. If you don't understand where we get this orbital, the formula of the orbital speed, you can watch the Mars video. Yes, it should be the Mars episode where I explained how we get the V bar is equal to the square root of gm over z, or gm over r if you're used to the conventional way. As you can see with the gravitational force and the accelerating force, which is the centripetal force there, we used r as the separation of the masses. But in this case, we're going to use z as we've been using as the same major axis. So we put in the values, same values that we looked at, that we used in the orbital period, are the same ones that we're going to be using here, as you can see. But it's just that the orientation is a bit different. So what we do is we assume that the gravitational force and the centripetal force are equal. That's how we get that formula. And then we just plug in the values, and then we get our 6,800 meters per second, which when we want to convert it to kilometers per second, we divide by 1,000 meters, and then we get our 6.80 kilometers per second, which is correct to 3 significant figures for some accuracy, but it's still fine if it's in meters per second squared. But just so that you can understand, 6.80 kilometers per second is the speed that Uranus takes or moves at as it goes around the sun, the average speed. It's not the exact speed that it is moving at each and every point in time, but we're saying that the average, because it accelerates probably and decelerates as it moves around, depending on some factors out there in space, which probably we are still yet to also find out in terms of what affects these planets. We're still studying them. For your own information, the James Webb Telescope brought back to Earth some images, very beautiful images of Uranus using the infrared lenses, and everything looks very beautiful. You'll see one of the pictures that are in this video later on as you get to read more about Uranus. Credit to NASA and the European Space Agency and the like. Okay, for the next variables, the radius, the circumference, and the surface area of Uranus, I'm not going to explain. You're just going to find out by yourself as you can read through and follow through with the calculations that are already there. It's pretty straightforward. Plug in the values and you get your answer. Now we'll look at surface gravity on Uranus. A point mass or any object on the surface of Uranus, although we know it's a gas giant, so probably it won't hold anything on it, but it has a greater force of gravity compared to some planets, some terrestrial planets. I think like Mercury, but as you can see, it's probably quite close to that of Earth. But it's a gas giant. It's basically a gaseous surface. It's not a terrestrial planet, or like what we see with the Earth, which is a terrestrial planet. But what we are going to realize here is that I approximated some values and I got 9.0077 meters per second squared as the acceleration due to gravity on Uranus. After doing my conversions and all the like, I used the Newton's second law of motion, mg, that's why you have mg there, and the gmm over r squared is the expression for Newton's law of universal gravitation, which is written at the bottom left there. So the same assumption we use for the speed, where we equate the two forces, is the same thing we're going to be doing here. We're also equating the two forces from the two laws that Sir Isaac Newton left for us, and we then get our g is equal to gm over r squared. And then plug in the values, but the mass that we're going to be using is the mass of Uranus, and the separation is going to be the radius of the planet. I think the diagram there can show you what I mean. Where the brown dot is, that's the center of Uranus, and that is where the mass is concentrated. If you don't understand that, you may need to watch the make video, the dwarf planet make, and some other videos like the Earth video as well. The previous episode, which was Earth, you may need to also watch that one. We recently did that one, so if you watch that one, you get to understand the phenomenon. But that's basically the idea of how we calculate it. So as you can see, my value is 9.0077 meters per second squared, or newtons per kg, depending on which unit and which equation you've used. But as you can see, other sources say it's 8.87 meters per second squared. So if you have managed to decode where the problem is in terms of approximation, I think it's a problem in terms of approximation. But if it's not, whatever problem it is, just drop your findings in the comment section so that we can get to correct that mistake. Otherwise, I think I'm done, and till we meet again with another planet, I think the only planet that's now left is to Neptune and beyond, which is the 8th recognized planet in the solar system after the demotion of Pluto in 2006. So yeah, there you have it. The calculation section is done, and till we meet again, cheers. More on Uranus. Bar graph to show which planet has the most moons. around Uranus.
Some kind of butterfly. Baby, you give me midnight. You whip up my appetite. Don't leave me here high and dry. Oh, but I don't wanna jinx it, baby. Let's not get ahead of my time. Oh, but I don't wanna miss you, baby. So I stand up and speak my mind. Oh. You're chilling when the rain. You're some kind of bird.